This is going to be a long video today because we're going to be talking about what is the Delta heat treat and low temperature tweaks for heat treats for the different alloys. We're going to be talking about the Kephart knife design, and we're going to be talking about how we optimize a heat treat here, like what the steps are that I use, that any knife maker or any person using a tool steel could use to optimize a heat treat for an application. The knives that we're looking at today are the Kephart. It's a 100-year-old bushcraft design. Horst Kephart came up with this way before I was ever born, but it's an ugly knife, but they work very well for what they're intended. And I happen to have some around, so I'm going to be looking at the CPM 3V with the industry standard heat treat that uses the secondary hardening hump. We're going to be looking at Delta 3V, which is CPM 3V, that uses the most refined low temp tweak for the CPM steel. We're going to be looking at AEBL, which is an entirely different type of steel, and just for shits and or just for grins and giggles, we're going to be using a commercially available, just a production Kephart knife. So what is CPM 3V, and why does it need to be optimized? 3V is a particle metallurgy super steel that was developed for tool and die industry, and this tool and die industry, it benefits from the finished part being the same dimension after heat treat as it was before. So you don't want part growth, and so your steel. Well, what is steel? Iron makes steel hard by forming a martensite, and so iron, it's you've got these metallic bonds. So the steel is held together not through covalent bonds, but through metallic bonds where all the different atoms are sharing electrons freely. It's why it's conductive. It's why it conducts heat well. And it's not a chemical reaction with carbon that makes steel get hard. It's at a high temperature, the normally body-centered cubic crystalline structure turns into a face-centered cubic structure where carbon atoms can move around and get stuck between, just physically stuck. They're not actually connected. They're just iron with carbon stuck between them is what makes steel hard. And so you can imagine this hard structure, which we call martensite, is less dense once it's got all that jumble of carbon stuck between all of the atoms. So that's a long way of saying that steel gets bigger after you harden it. Your tetragonal martensite is less dense. It takes up more space. And so the problem for people making tools and dies is their work is physically larger after they pull it out of heat treat, and so there's tool and die steels that are designed to minimize part growth, and they do this through a couple of ways. One is they're intended to stabilize a little bit of retained austenite. And I won't go into a lot of detail what that is and what it does, but I'll tell you that for a knife, it's not good to have in your knife edge because it's soft, but it does reduce part growth. The other thing they'll do is they'll take a steel and they'll design it so that it gets hard at the secondary hardening hump. So you can get this steel pretty hot. And there's a lot of advantage to being able to get steel hot in use. You've got there's tons of reasons why you would want a particular tool to tolerate heat, but the secondary hardening hump, you'll get a cubic martensite up at these temperatures that it's a little bit more compact, it's a little bit more dense, it's a little bit more, I guess, orderly of a crystalline structure. So you're looking at a structure that does pretty well on a tool. And it has, because it's highly tempered, it's kind of shrunk back pretty close to where you started. And so in a tool and die steel like 3V, or like a D2, which is where we first started messing around with these low temp tweaks, you will have an opportunity to utilize a heat treat that does not use that secondary hardening hump. And the reason you might want to do that is because you're able to keep the carbon tied up in the martensite, which is where you want it. That martensite, if you've got really hard, strong martensite and slightly smaller carbides, you're going to have a structure that is able to hold an edge better at the narrow angles of a knife edge. The steel is going to be stronger at a microscopic scale, and it's something that may not matter. You may not notice it if it was a big stamping die or a drawing tool where, you know, abrasive wear was a cohesive wear, or some other mechanism where the tool breaks down is in play. But in a knife edge, it's kind of weird, because steel is a product that in most applications it doesn't physically break, but in a knife it's a weird application because it's a very acute geometry taken to a very small apex, and normal use it breaks, like chipping, crumbling, rolling. You're exceeding the yield strength. You're physically breaking it. It's not a typical application where it is expected to last for a long time without, you know, breaking down. So knives are kind of a unique application for steel, because they stress it in a way that they're not stressed in other applications. So your secondary hardening hump, which is great for tool and die work, maybe isn't perfect for knives. And so with the low temper tweaks, there's a couple things you got to do differently. You're going to have to address retained austenite with some other mechanism other than just hitting that secondary hardening hump to convert retained austenite. And so quench rate becomes more important. Quench rate matters for a couple of reasons. One, the faster you quench, you're maintaining higher strain energy going into martensite finish. You're going to be able to convert more of that retained austenite, or it's not retained austenite at that point, it's just austenite. You're going to be able to convert more of that into martensite. The reason this is important is because even if you convert austenite into martensite later on through, you know, maybe after a snap temper or through the use of secondary hardening hump, you're still going to have issues with it converting into something that's not the same martensite that you would have got had you just quenched into martensite to start with. So you've got, you know, you can get pearlite, you can get bainite, you can get all kinds of structures other than martensite, but you can even get martensite, but it's not the same as if it had been formed at the same time. So if you're going to use one of the low temp tweaks, you're going to want to use a relatively rapid quench. And one of the things that'll do for you is it'll give you superior corrosion resistance. It's not why we do it, but I mean, sometimes it is why we do it, but that's not why I do it. The superior corrosion resistance comes from that carbon not reacting with the free chromium in the steel, and so you're able to keep more of that chromium free where it can give you corrosion resistance rather than having it, that's already getting a little bit dull, rather than having it turn into chromium carbide. So when you're doing a secondary hardening hump free, or you're doing a low temp tweak, you want to make sure that your quench rate is fast enough, and you also want to make sure that you're quenching to martensite finish, which is kind of an arbitrary number. It's not there's not really a martensite finish. You're never going to get 100% martensite, but there's a good rule of thumb that if you can get below 100 degrees Fahrenheit, and do it without temperature reversals, you're going to be able to get your best martensite conversion. So anytime you're doing a low temp tweak, you want rapid quench and quench to cryo, no snap tempers. That's a mistake that the industry has been making for a long time, which was they were putting a snap temper after their quench because that's best practice if you're making tool and die, if you're making landing gear for an aircraft. If you're making any normal product, you want to put a snap temper in there before you go into cryo, but that is not the case with knives. And in fact, this is a problem you can run into with heat treaters that aren't really set up and experienced doing knives, is they can have their temperature in their oven reversed. They're using these vacuum ovens, and so you can get a pretty good quench, and it's, you know, so far so good. And then you leave it in the oven, and the oven's got some thermal mass, and the temperature reverses, and you'll stabilize some retained austenite. So there's a lot of pitfalls, a lot of things that can go wrong. So if you're using one of the low temp tweaks, you need to make sure that your heat treater is doing it right. And if you're doing it yourself, you're doing a plate quench, you're in pretty good shape if you've got a design that has good contact with your plates. And so I would recommend anybody who's getting into this, start by doing it yourself. Use your own oven, pull your work out, do a good plate quench, make sure the foil's not in the way, you're getting good contact, and you can get really good results doing it yourself. And then when you send stuff out to be heat treated, you can compare what you got with what you did yourself and see if the heat treater is doing the job right. You cannot just measure the Rockwell hardness and see whether or not you got a good heat treat. That just tells you the depth of a dent of a diamond indenter. It's not telling you anything about your microstructure. So the way you can tell if your heat treat did what you wanted it to do, or if you're developing a heat treat and you can see whether or not one heat treat is working better than another, is to do what I'm doing here, which is cut repeatable media with your knife that you're wanting to evaluate and compare it against other knives as standards. And so this is a non-quantitative approach that will give you this is better than that, but it won't give you a number. It's not like a Rockwell hardness number. It's not like sheets cut in the Carothers test. It's not like a IZOD impact number. You're not getting a number. You're getting a comparative result. And so it's not ideal when you're talking to someone and like, well, this is why my knife is better than this knife. It's because it has it has better edge retention, better edge stability. It has this, that, or the other that's better. I wish there was a quantitative number, but to my knowledge, there is not any measurement that you can make that gives you a hard number that will tell you whether or not you're getting the edge stability that you want. And this is the reason we use the low temp tweak in the first place, is edge stability. So knives go dull cutting soft abrasive stuff like cardboard, and you can see that very easily. And so what I'll do when I'm doing this, and I'm not shooting a video, is I'll cut all this cardboard, same amount of the same cardboard, and I'll look at them next to each other under bright light and under magnification, and I can kind of start to see which ones are going dull and which ones aren't. But what you'll find is that a simple steel, like a carbon steel or a relatively simple steel, AEBL, is going to start going dull faster. And your high carbide vanadium tool steels like 3V are going to hold an edge better in something soft and abrasive, but you're not going to see any real difference between, in my case, the Delta heat treat or your low temp tweak and the industry standard that uses a secondary hardening hump, because the abrasion resistance is largely baked in. There's not a whole lot that you can do about that. It's tied to the secondary carbides. You're not doing anything to the secondary carbides. You got, I don't know, probably 10% vanadium carbide by volume in one of these things. It's going to be abrasion resistant. It's the edge stability that causes issues with your edge stability that will cause poor edge retention in hard use, or what I would consider normal use. And it's an optimized heat treat, such as one of the better low temp tweaks and our Delta heat treat, that, you know, here it's all the same difference. But when you start getting into maybe you're carving on a piece of wood, this is a piece of well-seasoned pressure treated pine board. You know, it's not a difficult material, but if you're camping and you're peeling the bark off of a stick, or if you're in the field and you're peeling insulation off the wires, and or if you're in a shop and you're deburring parts, this right here, this kind of cut where it's a sliding cut and you're kind of getting some edge loading, is where you're really going to see the difference in edge stability. And so a knife like this AEBL, which doesn't have the best abrasion resistance, like it was shaven hair before I got started here, and it's already not shaven hair. It didn't do fantastic in the cardboard, but a lot of people don't cut a lot of cardboard. A lot of people go camping and there's not a lot of cardboard in the woods. They're doing things that's putting stress on the edge, and the edge stability of AEBL is actually quite good. So I would expect this AEBL to stay sharp better than this CPM 3V in this kind of use. Now that's ironic, because you would think something that takes as long as 3V to sharpen compared to AEBL would stay sharp longer, and it does in cardboard. But what we found, and this is the reason we developed the low tint cleats in the first place, what we found is in this kind of application, it doesn't really do any better than simple steels. It needed some work. And so the Delta heat treat and any of the low temp tweaks, if done correctly, can improve your edge stability, because you've got harder martensite. There's more carbon in your martensite. You've got slightly finer carbides because you're not developing as many secondary carbides and you're not growing your primary carbides. And because you're addressing retained austenite in the quench, you've got a little bit more of a homogeneous microstructure. You don't have a mix where, well, this is martensite formed in the quench, this is martensite formed in the temper, this is, bainite or upper bainite, or you get some, cementite and ferrite. Like, you're going to get a mixed structure versus form it all martensite to start with. You don't have all those little soft spots that behave like the perforations in a postage stamp that make that edge fold over. So whenever I'm doing a workup, I'm doing these tests like this, and what you'll find, and I'm not going to stop the video now because I know what I'm going to see, but what you'll find is that after doing this kind of a cut, you'll start to see a difference. And these are all sharpened at 18 degrees, no, I'm sorry, these are all sharpened at 20 degrees per side, which is what this model is ships at. So this is 20 degrees per side. If you'll make it 18, go a little narrower, when you're doing your development work, it'll make these little differences stand out. So if you do a heat treat and you try something and you want to see, well, did this make it better or worse? You've got your standards, you've got the ones you've already done, you go to the new one, and you start doing this stuff, it'll start to become apparent. Hey, this made it worse, or hey, this tweak made it better. There's a lot of tweaks that you might not even think about that matter. Like something that I never would have thought would matter is for these steels is how, they spherodize this steel, and the condition of the steel when you get it, it can affect the heat treat response. And I didn't expect that. I found it when I was practicing when we were doing a development of our pre-quenching. Pre-quenching. What is pre-quenching? All right, pre-quenching. Pre-quenching is something that I was doing with D2 to do grain refinement. Pre-quenching, it's kind of what it sounds like, but it's not what most people think you mean. If you take, let's take D2 for example, because that's a steel we've talked about, on the internet before. So D2, if you take it up to let's say 1750 degrees, which is below its normal austenitizing temperature, and you hold it there and then you quench it, and then you go up to, let's say, 1875 degrees, which is a little high, but maybe that's where you process it. That might be where I process it. You will find that second trip up, it doesn't need to soak as long. And so this is pre-quenching. It's in the literature. It's pretty well understood that pre-quenching D2 in this manner, if you do it right, can get you very fine grain. And if you do it wrong, you can get explosive grain growth. And so it's one of those things that you kind of have to look for, and don't just assume you did it right. You actually got to kind of experiment, find out where that becomes a problem, and go back. But one of the things we found when we were doing pre-quenching was that your austenitizing time is shorter the second time, and that actually had some effects that we weren't exactly sure why, but there was some benefit to it. We don't know what was happening, but in our testing we found, hey, that makes a difference. So there's all kinds of things that you will find that you don't know matters, and until you're doing side-by-side testing like this and controlling your variables, like you need to have exactly the same edge angle, because 18 degrees is way different than 20, is way different than 22 when you're looking for these small effects. You got to control that precisely. So when you're optimizing a heat treat, there are a lot of variables, and there's variables that you're not going to expect to see that matter. So what we'll do, so I've cut some cardboard. I already know I'm going to see a little bit of wear in the simple steels. We cut some seasoned wood. This is how I do it, but I don't usually do it just talking to somebody. I'll stop and we'll look at it under magnification. So at this point, you will start to see some differences, but the Osage orange, this is a really hard piece of hardwood, and these cuts where I'm putting it in there and leveraging it out, that's where the edge damage really starts to become apparent. So this cut right here plays hell on any steel that has issues with edge stability. And so the Delta heat treat right here, which I mean I can already tell you it's perfect because we've done this a bunch of times, but the Delta heat treat does really well. And then this guy right here, which is the standard heat treat, uses the secondary hardening hump. It will have inferior edge stability in this kind of a use where you're kind of putting it in something really hard like this and peeling it. And so if I look at this under magnification and I hit it with a flashlight, I'm going to see some trouble there. Oh, the edge is dented up and kind of glittery. You're not going to see it in the video. We'll have to stop it and shoot a picture, but give me just a sec. We'll do the rest of these. But yeah, so this guy right here, which is the industry standard heat treat, took some damage, which is expected. This is not the first time we've done this. I'm gonna do that to these guys also. Where was I didn't make this knife. It's just a bought it on Amazon or Kmart. It's a commercially available knife, and it's a really good knife for the money. It's a good value. These are inexpensive, and it's a little bit bumpy there. It didn't like that, but it's not bad. It held up pretty good. I mean, for the money, it held up really well. And then this is the AEBL. All right, and yeah, that held up really well too. So AEBL has very good edge stability. Probably has the best edge stability of any of these, even though it doesn't have the best edge retention if you're cutting something abrasive. Delta 3V, it's just, I mean, it's perfect. It's not, there's nothing there. This Walmart knife, now interestingly, I was putting some force on it. These scales moved around, right? So that's one of the, I'm glad that happened because I can talk about, this is one of the differences between my knives and some knives you might buy, is that these are not pinned on. I mean, they're pinned on, like, but they're not, the pins aren't like tight, so the scales move around. Mine don't do that. And this 3V, which, it's going to do well in this abrasive stuff, did not do well in these lateral cut tests. You can just take my word for it, because what we're about to do is going to really make that stand out. The hardwood damaged it, but a steel bolt is gonna really. So this is where we start kind of getting outside of the realm of normal use. And like, well, why would you want to cut a steel bolt, right? Well, nobody in their right mind is buying a nice knife like this and using it to cut steel bolts. But if you, as a knife maker or somebody that's seriously evaluating one of these, wants to get an idea of like, okay, well, everything else is equal. These are all the same geometry. What can I learn by cutting on a steel bolt? And you'll pick up some ideas about it. The not the quality of the heat treat, but just the characteristics of that particular steel. And in this case, some of the trouble that you'll get using the industry standard heat treat instead of a optimized heat treat. So there's a when I say optimized, people might think, oh, you just found the right tempering temperature, or you found the right austenitizing temperature, and that's not it at all. It's you found the right material condition to start with. You found the right quench rate and quench depth. You've got your cryo steps, the timing of the cryo figured out, and you're ultimately going to try and get something that has the best edge retention, and edge stability is a big part of that. And you're going to do that by not just balancing your characteristics. Yeah, that actually didn't do great in the steel. So this is maybe a little bit softer than these, but you're gonna. It's not just optimized in the sense that it's you found like just the perfect hardness. That's not it at all. It's you figured out the heat treat that's going to give you the best microstructure, the best set of properties. Yeah, AEBL does. Yeah, that's AEBL. AEBL does pretty good, better than I thought in the bolt. So, in all of these, the Delta 3V is by far the best in carving slivers off a steel bolt. Now, these are all the same hardness. I should have mentioned that. So, we actually made these 3 samples, right? So, identical geometry, sharpened at the same angles. They came out of the 3V came out of the same sheet of steel, so that when you see a difference in the behavior of that steel when you're carving slivers out of a hard object like that, it's the heat treat. And they're the same hardness. This is the thing that some people have trouble wrapping their head around. This measured at 60.5, just a hair over. This measured 60.5, just a hair under. So these are within a fraction of a point of the same hardness, same steel, same geometry, and not this one, this one. They're the same, but they behave differently in a hard object like that steel. So the next thing we're going to do here is we're going to cut some bolts. All right, so let's this is like, I don't know why anybody would do this, but it'll tell you something. So, all right, so first up we got a piece of AEBL. This is a pretty tough stainless steel. Its only weakness is that it's not got the best abrasion resistance. It's a pretty simple steel. It's as good as what Horace Kephart would have carried back in the early 20th century, but it's not fantastic by today's standards, but it's pretty tough. And so I think it's going to cut this bolt and do surprisingly well. So let's see what AEBL can do in a 1/4-20 bolt. We'll take pictures after we finish this video, but I'll tell you it's very little edge damage. This is in good shape, nothing blown out, held up just fine. All right, let's look at Delta 3V. I already know how this is going to do because we've done this many times, but Delta 3V will go through a 1/4-20 bolt without any real damage. Delta 3V, no real damage, what we expected. And let's look at, this is CPM 3V that has the secondary hardening hump. So this is your industry standard 3V. Got good abrasion resistance, pretty tough stuff. It's nice steel. Doesn't have the best fine edge stability. So let's see what this does. Uh-oh. All right, so we have some definite, we'll take some pictures of this. So this is 20 degrees per side, and I want to talk about that. This is not 20 degrees off the other bevel. A lot of people that have a sharpening kit that has like a wedge in it think they know what 20 degrees is, but they might be looking at 24 degrees. This is 20 degrees off the center line of the knife. So this is the angle that my mom sharpens her kitchen knives at. So this is pretty acute for something you're running through a bolt, but it's not good on the secondary hardening hump. And let's look at this other knife. We haven't run one of these through a bolt, right? Let's see what happens to this guy. This is just a Kephart that I bought at Walmart. Let's see how these guys do. Ooh. Yeah, that's all right. It's got a catastrophic edge failure, so that didn't do well. So that's how we develop a heat treat, or like that's some of the steps that we do when we're, you know, figuring out what tweaks help and what tweaks hurt. And that's the difference between the industry standard heat treat and the Delta protocol. And I hope this explains what we do and why we do it.